Yeah, so this is, of course, a conference about programmable cryptography, and we're programming ZK in particular, but I kind of want to talk about all of it. This is the background we use for our slides in our website, and it reminds me of something, which is a book. Has anyone read this book? Anything else by Greg Egan? Permutation City is another great one that he's written, which is kind of a Bible for thinking cryptographically. Anyway, we'll get back to that in a minute. So why are we here? What problem are we solving, right? In some sense, we're solving the problem that people lie on the internet. Of course, before the internet, I don't know if any of you remember, people also lied. And we're trying to figure out ways to make that not impossible, but to understand when we can believe, right? When we can have truth, and even more importantly, kind of transitive truth. And of course, you can throw computers at it, but they can just lie faster, right? Like things can spread faster with social media. AI can let us generate unlimited amounts of false information. And as a society, we need to figure out strategies for dealing with that, for defending from that. And that's just part of what we're doing, but I think it's important. Historically, the solution to people lying, whether it's in commerce or identity, is trusted third parties, right? Asking Facebook to identify you, asking a bank to track your balance instead of taking your word for it. And of course, a lot of what we're doing with cryptocurrency and cryptography is replacing trusted third parties. In some sense, the most important thing ZK can do is to disintermediate trusted intermediaries. And you've seen, if you've been here for the whole week, you've probably seen these pictures a couple of times from Szabo's 1997 paper. So, the first situation is we have a mutually trusted party, a trusted intermediary that we use to solve this problem. We give it secrets or private information. It keeps those secrets for us, we hope. It doesn't lie, we hope. And it's secured by its freedom, right? It can be imprisoned if it does something it shouldn't do. And it's kind of chaotic. It's kind of corruptible, right? Like it's subject to regulatory capture and all kinds of other capture. And another idea I want to kind of push on today is that in some sense, it's not the ground state, right? It's kind of a high energy way of tracking what needs to happen and of tracking the flow of information. And we've been working toward replacing that with a mutually trusted virtual computer on the other side. We've built that computer, which is an insane accomplishment, right? And it feels somehow like that is the ground state. Like once you're in that computer, composability is easy, trust is easy, it's somehow lower energy, right? But it feels like that state, although it's really powerful, is spreading too slowly, right? We can do some things, but it's not as scalable as we'd like. It hasn't taken over the world with the rapidity that we've hoped, or at least that our investors hoped, right? So I think about it as kind of like that's a crystal that we've dropped in, and we're trying to grow that crystal of verifiable information with programmable cryptography. This is another diagram we like to use. So in the context of the EVM, there are the things that the EVM can do in the red circle, and we use a combination of, we use math, the math of ZK, to expand kind of the legitimacy circle to a broader set of operations and a broader set of affordances, more complex functions, and things that you can do with ZK or with particular our package EZKL. So we're trying to expand that boundary with programmable cryptography, but there's a problem here. What's the problem? It's sort of the programming, right? It's 2023, nobody programs anymore, at least according to my Twitter feed. You just show a few examples to ChatGPT, and the app is built and you're done, right? Now that's an exaggeration, but there's some truth to it. We have a lot of work to do in sort of growing that scope of verifiability. And to do that, we're going to need a fast development loop, right? We need to be able to try experiments extremely quickly and see what happens. We need to search market spaces. We need to look for solutions. We need a fast development loop. And we have AI now. We want it to help us search that space, right? Build apps for us, be able to train AIs instead of writing programs sometimes. So, what we built EZKL for is to turn an ML or AI model into a zero-knowledge proof, deploy it on the EVM verifier, and that way we can extend and explore that space by training, by leveraging AI, as well as by writing programs the old-fashioned way. Right? Also helps you write programs the old-fashioned way, but it's kind of really exciting to think about what if you don't have to write those programs. You can just explain what you want and get the same result. So what is EZKL? We aim it to be the easiest and fastest development loop in ZK. You write an AI model or other app logic in Python. We use Rust and Halo 2 to transform it into a prover and verifier. And then you can deploy it with Solidity verifiers and use TypeScript and JavaScript for the front end. Open source is very important to us. So this has been open source and built in the open, in fact, from day one. But we do have some backend services that can help with proving and tracking your model if you don't want to do it. We like to never kind of talk, but just hand you stuff. So one of the things we do is make it possible to do everything from a Google Colab notebook. Then you can spin it up right now if you wanted to and start to produce proofs. And there's lots of, that's kind of scalable in the sense that you don't have to ask us permission. You just can fire it up yourself. And we've done a bunch of other scalability things, like letting you split proofs up so that there's no upper limit on the size of the models you can prove. And just this week added GPU proving, which you can also do from the Colab notebook. You don't have to find a GPU or rent one from us or anyone else. So you can do, one of the problems we found as we work with people is that there's a lot of fiddly knobs in ZK, and sometimes you can really get stuck in getting started if those knobs, they add a lot of complexity, and you want to not have to deal with it. So what we've done is put a bunch of sensible defaults and automatic calibration into the system so that you can produce a reasonable setup without having to fiddle with it manually. You can set up the circuit from Python. And this is what it looks like to code it. So if you've ever written PyTorch or TensorFlow, you just write normal PyTorch or TensorFlow, and in some cases normal Python, and then we train it, and then we throw it into the compiler, and you get out something that's provable. You can also use traditional data science techniques. So this is an example from scikit-learn of a gradient boosted tree. So we support a bunch of that as well, which is interesting for lots of applications. People often ask us what models work. So one set of models are neural nets and vision models, convolutional neural networks, multilayer perceptrons. We also support a variety of decision trees, random forests, gradient boosted trees. We do support transformers and small large language models. We aren't quite to the point of llama yet, but I think that it's now just a matter of how many GPUs do you have, and no one's done the experiment. So if anyone wants to do that, let me know, and we'll help you. It will be a really fun announcement, whoever gets to it first. And as I said, we do a lot of classical statistics and data science. And if it doesn't work, it's a bug, let us know. We also have, as I mentioned, a backend. So if you want, you can actually just take a model and upload it to the backend, and it will produce a prover verifier pair for you. You can request proofs and download verifiers. And finally, you can prove and verify in a mobile browser in milliseconds for small models. And if you were at Casey's talk a few minutes ago, you can also program the ZooPass that you've used to get access to Devconnect using EZKL. So all that, to repeat something from Vitalik's opening talk, is that we're trying to make security in the sense of ZK cheap in development time. Right? The tighter the loop we can make it, the easier we can make it for you, the faster we can all explore that space. And to return to another thing from Vitalik's talk, people often ask how big is the overhead, and the truth is that we're in a multi-year process of trading programmability and overhead for less developer time and better security. 1000x or more has actually been fine, right? Like we went to the moon on less RAM than it takes to load a web page today, and we've been able to do a lot more. So in the context of programmable cryptography, we've seen this transition that's been talked about a lot, which is before we had, when you want to make a new application, you create a new cryptographic protocol. You hire some mathematicians, you do a ton of work, maybe it takes a couple of years. Now we're at a point where when you want to create a new application, you don't need to do that. You can just write circuit code in Circom or Halo 2. And recently, kind of now plus, we're at the point where you can write when you want to write a new application, you can express it in a higher level language, like PyTorch or JavaScript, for example, in Mina. And now I think there's an even better thing we can do, which is to return to it's 2023, nobody programs anymore, which is you want a new application, just train a new model, right? All we need to know now is not cryptography and circuit languages and everything else. You just want to know what the application should do and give it an example. And one example of that that we've talked about a couple of times this week is tic-tac-toe, right? So Jasim in the audience built this. This lets you take the following kind of insane approach to tic-tac-toe. I want to make an on-chain tic-tac-toe game, but I'm lazy and I don't feel like programming the rules of tic-tac-toe. They seem fiddly or they're annoying, right? So all I do is enumerate a whole bunch of valid games, train a neural network to decide whether that game was a legal game or not, and then let it evaluate the games, right? So that seems kind of nuts in the context of tic-tac-toe because we know the rules of tic-tac-toe, right? But there are a lot of other situations in which we don't know the rules. So for example, if you want a smart contract to read human legal contracts and make a decision, you could take a similar approach. And there's no fixed rules. We need the soft logic of AI to be able to accomplish that. So for a slightly more down-to-earth example, again, referencing something from Vitalik's talk about DAC, so defensive technology, is the problem of context provenance. So I started out talking about misinformation and the spread of fake images. That's become something that went from a theoretical challenge to something that is really serious, right? Like now we're in a place where you kind of can't believe anything you read and you can't believe anything you even see. You have to figure out some other way to verify that information. And if the source is verified, ZK is something that can come to the rescue. So of course, when you see a picture published on Twitter or on a news site, it's never the raw original picture. It's the picture passed through a series of image processing algorithms. Sometimes those are very gentle, we're just a gamma, we crop. Sometimes they're more severe, right? So we might take a camera. This is a camera that Leica just launched that costs about $10,000, and it signs every picture it takes with a digital signature. So you can take a picture, you can prove what transformations have been applied. Maybe we touch up the person's appearance, we apply a sketch filter, and we remove the background, right? We haven't changed the semantic content or who it is, right? So here's an example. You take a picture with Leica of somebody, and then you use EZKL to prove the transformation, improve his appearance, include a sketch filter, remove the background, and you get out that image, which is somehow the same, maybe a little different. Another kind of defensive technology that you can build with ZKML is what I like to call defense in depth. And this is actually the original scenario for which ZK was developed. The first time I learned about it was in 2015 at an Air Force meeting that I attended. But let's not talk about the Air Force, because that's a little bit complicated. Let's talk instead about a Roomba. So imagine that you have a Roomba in your house. The Roomba sees an obstacle, or it's looking at the top of the stairs, right? It's looking down the stairs, and it's wondering, I'm confused by this situation. Should I drive down the stairs? Should I drive over this obstacle? Should I crush the teddy bear or drive down the stairs, or should I not? It takes a picture, sends it to Amazon. Amazon makes a decision and says, go for it, or turn around. Now, the problem with that is it's vulnerable at many levels, right? If I control the Roomba, then I can give it wrong instructions. But also, if I control the channel, if I've hacked your router, or I otherwise control the channel between the Roomba and the server, I can give it wrong instructions. If I control the server, if I hack the server, then I can give it wrong instructions, right? But with ZKML, what the Roomba can do is to take a picture, hash the picture, it knows the hash, and it can have a verifier deployed on it. Verifiers are very low resources. The Roomba is like the blockchain here. Sends it to the server computes an action and returns it to the Roomba. And in this way, even if the channel is compromised, even if the server is compromised, there's no way for the Roomba to get incorrect instructions, right? And this is, of course, important whenever the actuator at the end is making a consequential decision, right? Should I drive down the stairs or not? Should I knock over the vase or not? And I'm sure you can imagine other even more serious consequences that can come from a robot at the end of a server. Okay, so the last application I want to talk about is around money. And there's this a phrase, all about the money, that people like, right? Like, oh, they're focused on the money, it's all about the money, follow the money, just get money. Why do we care about money, right? It's just like one way to convince someone to do something. And I'd argue that a lot of why we care about money is that what we really want is a zero-knowledge proof, okay? Oh, that sounds sort of ridiculous. What do I mean? So what is money? It's like, I do something for you, you do something for someone else. When I do something for you, you want some kind, or you do something for me, and I want to give you some kind of marker of my favor. I want to give you a form of thanks. And the best kind of thanks is one that you can then use to give someone else, right? And you want that thanks to not depend on the whole history of all of the transactions that led up to it. You want that thanks to be transitive, right? You want it to be a zero-knowledge proof. So you can think about the system that we've built around the financial system as really something to enforce this transitivity, to make it possible for me to say thanks to you, for you to take that thanks and pass it to someone else, and them to pass it to someone else, right? And we combine, all the invoices or all the things we've ever done for someone else, all the things others have done for us, receipts, times I bought dinner or a mango or whatever, and we outsource to a trusted third party, to go back to the beginning, to make sure that those transaction histories are transitive, that all the times that we've given someone a token of our appreciation, that token can be spent again. And then that financial institution does a check. Given all the good and bad deeds that I've done in my life, if I weigh them, do I deserve a mango? Do I deserve a yacht? Right? That's their job. So it's really about transitivity. And we figured out a way to replace that trusted intermediary, right, with blockchain. And that was an incredible accomplishment. This was the first version, in some sense. But one of the things I want to point out about this is I think that this is not the end, right? Even this is not the end. This is programmable, but it's still skeuomorphic, right? In other words, we've taken the idea of tokens and ledgers that was developed in the 14th and 15th century, and we ported it to our new technology. But our new technology is much more powerful than that, right? We can't just prove ledgers, we can prove anything, right? We can have an AI that looks at all the history of everything I've ever done and decides whether I get the mango or the yacht. Not that we should, but we could, right? So we have this technology, it's built of consensus, it's built of signatures, it's built of zero-knowledge proofs. I think the first thing we thought was cool to implement on was a ledger, but that's just because we're copying the past. And I think what happens next is going to get extremely weird and extremely different. So you could call that the cryptographic internet, right? Programmable cryptography, interoperability. You could narrow scope a little bit and talk about that as verifiability, right? So we take some small kernel of verifiable, trustable information that we've built from blockchain, and we expand that to encompass more and more of the economy. Either that's scaling blockchain, or that's using zero-knowledge proofs to make much bigger statements that concentrate, that tie back to blockchain every once in a while. And so let me explain the reference to this book, Child's Ladder, by Greg Egan. So in this book, it's a science fiction book, there's a discovery of a new ground state. So the idea is space-time has some state. You can think of space-time as maybe like a lattice. That's not, but something like a lattice. And scientists figure out that there's a change you can make in the lattice that makes it lower energy, releases some energy and drops. And then that new ground state, lower energy state, starts to spread at the speed of light throughout the universe, right? And that's in the context of space-time. And I would argue that that's sort of the situation we're in now, right? So we found this new ground state. It took us a long time and a lot of work, and we found this new ground state. And now that crystal can kind of start to spread throughout the economy, right? In other words, this verifiable internet, this computational internet, is a lower energy state than today's trusted intermediary. Hey, it's just my opinion. We constantly have to weigh all these opinions and spend a tremendous amount of human and computational effort and economic effort in deciding what's true, right? But in the center, we don't have to spend that anymore, right? So Ethereum in this context is the seed. It's that new spot of lower energy space-time. And programmable cryptography is the vacuum collapse that results, right? As this verifiability spreads throughout the entire economy and unleashes a tremendous amount of value. That's all. Thank you.